let's go to the last talk in the session, again by Satoshi Yoshida. This time on the analytical lower bound on the number of queries to a black box unitary operation in deterministic exact transformations of unknown unitary operations. Please.
Sorry. Okay. Thanks very much. So in the second talk, I will talk about our recent work, and it's based on this archive paper, and then this is a joint work with Tatsuki and Murao. And after the submit, so this is the original title. I submitted to the QIP, but I realized that this title is too long, so I just shorten a bit. Yeah. So like this. So it's kind of analytical lower bound on query complexity of some transformation. I will explain in more detail. So I will first talk about the kind of more high-level overview of this line of research. So this is about the higher order quantum operation, and this is to mimic the higher order function in the classical information processing. And this is the following concept. So usually in the classical information processing, we apply the function on bit sequence to do some information processing, but we can also apply function on function. It's called a higher order function, and this can be useful for some programming language. And basically, we can define the quantum version of this one, and basically, by replacing bit sequence with quantum state, we can obtain the quantum operation. And by replacing function with quantum operation, we will obtain the higher order quantum operation. So this higher order quantum operation is a transformation of quantum operation. And in this work, we consider the universal transformation. And the universal transformation is basically the following one. So I will first explain for the quantum state. So given some unknown quantum state, the task you want to achieve is to obtain the function of the input state. And the important thing is that this is not the point-to-point transformation like preparing a quantum state from the Ket0 state. And the example of this universal transformation is a state cloning, which is to implement the row tensor row, or universal node, which is to implement the orthogonal state to row. And we consider the higher order version of this one, which is basically universal transformation of quantum operation. And instead of quantum state, we have an unknown quantum operation as an input, and we want to transform it to a function of the input operation. And in particular, we consider the case where the input operation is given as a unitary operation. An example of this task is a unitary inversion, which is to obtain the inverse operation from the input unitary operation. And this task is interesting because it somehow simulates the time inversion of the Hamiltonian dynamics. And it has some applications. So it can be useful for quantum control or learning some properties about the Hamiltonian dynamics. Okay. And to implement such a higher order quantum operation, we can basically utilize a object called a quantum comb. And quantum comb is basically the quantum circuit with an open slot. And in this figure, each box represents a quantum operation, and we have an open slot in between. And in this open slot, we can insert the input operation to obtain the output operation. And this is an example for the single slot case, where you can just insert one input operation, but you can also consider the multiple slot case. Okay. And in this work, so we consider the universal transformation, but for the universal transformation of states, there are many no-go theorems, and basically it's impossible to do such kind of transformation without paying any failure probability or approximation error. And but so the natural question is, how about for the universal transformation of unitary operation? And surprisingly, so first, if you just have a single query to the input unitary, many transformation is still impossible. So for instance, inversion is impossible. But the recent work have shown that if you have multiple queries to the input unitary, and this is actually given by d to the d square for the dimension of the unitary, then you can implement the inverse operation. So in the higher order world, universal transformation is possible. And there are other possible transformations, like complex conjugation or transposition. So if you have such a possible transformation, the natural question is, what is the fundamental limit of such a universal transformation of integral operation? Because intuitively, it seems like impossible, but it's possible. So you want to show what is possible and what is not possible. Okay, so this is the outline of this talk. So first, I will show you the problem setting where, what we are solving. And I will show the main result and the proof technique and extending to some, more general settings. Okay, so in this, work, we consider the universal transformation of an integral operation. And basically, this is a task where you have an input integral operation drawn from a Hall random distribution. And you don't know what this unitary is. And the task is to implement the function of this input unitary u, where I write the f. And basically, what you can do can be represented by the quantum comb. And in the quantum circuit, so basically, it's represented by this. So you can just insert integral operation v1, v2, v3 in between u's. And you want to implement the f of u as a result. And I will introduce one notion about the query complexity of the function, and which is defined as a minimal number of queries to implement the function f using this quantum comb. Yeah. And the question is, what is the fundamental limit? And in other words, what is the lower bound on the query complexity of this function f? Yeah. And we have some technical assumption on this work. So for some technical reasons, we assume that this function f is differentiable, which basically, in a sense that if you insert the e to the I epsilon h on the this function, you can define first derivative given by a g, and this function g is basically a linear transform for the Lie algebra of SUD to SUD. But the known results, in the previous work, all satisfy these assumptions. Yeah, and there is some previous work on trying to show some lower bound on query complexities. And the first method is to utilize some polynomial method, and which is to utilize some linearity on the quantum theory. So if you have n query of unitary, what you can do in the quantum theory is just the nth polynomial on u. So if you can bound the polynomial degree of the function, then this will give you the lower bound on your query complexity. And the second method is to utilize some topology. And this is very specific to the one task called controlization. And in this previous work, the authors have shown that by using some property on the continuous function on unitary group, you can show a no-go theorem for the controlization. And the third method is some numerics. And this is basically to utilize, consider the optimization problem of the fidelity for a given dimension and the number of queries. But this previous work have some problems. And the for the problem for the first method is it basically gives the non-tight bound. And the second method is very specific to one task, so it's not universal. And the third one is not scalable because you have a limited number of computational resources, so you cannot do for infinite. So we need a tight and a universal and a scalable lower bound to this task. Okay, so I will show the main result. So basically, the query complexity of the function f is lower bounded by this SDP, which is a optimized minimization of this trace beta, and this beta satisfies some positivity constraint. And in this positivity constraint, the information about the function f is encoded to the operator jg, where the jg is the Choi matrix of the g, and the g is the first derivative of the function f. Okay. And I have some remark on this result. So the first, this result can be applied to any differentiable function. So it's universal in a sense. And the second remark is that the right-hand side has a SDP, and it's okay. It's also numerically solvable. And the important point is that this SDP does not depend on the query, number of queries to the, number of queries. So as long as if you have a finite dimension, you can solve this one numerically as well. And the third one is that this lower bound actually gives a tight bound for some cases, which I will show you in the next slide. Okay, so by applying the SDP lower bound to 3 instances, inversion, transposition, and complex conjugation, we have obtained these bounds. And to show the to look at the tightness of this lower bound, I compare this bound with the minimal known query numbers in the previous work. So for the inversion, our lower bound shows that n should be larger than or equal to d squared. And there is a previous work showing that if you have basically order d squared calls, you can implement the inversion. So basically, it gives you the matching lower bound. And for the transposition, our lower bound gives a linear scaling with d, whereas the minimal known number is order of d squared again. So it's actually not tight. And for the third one, complex conjugation, our lower bound gives d minus 1, and there is a protocol to implement the complex conjugation using d minus 1 query. So it's actually tight. Okay. And also, we also have a bonus result on the no-go theorem on catalytic transformation. And what the catalytic transformation is. So it is to utilize some catalyst state in the universal transformation of a unitary operation, and it was observed in the qubit unitary inversion protocol. So basically, in the qubit unitary inversion protocol, it utilizes 3 calls of input unitary plus the choice state of unitary to implement inverse of unitary, and you also, obtain the choice state of unitary in the end. And so basically, this choice state of unitary, acts as a catalyst state. And interestingly, if you don't have this catalyst state, it is known that this inversion is impossible. So this catalyst state is actually useful. But our theorem basically rules out the possibility of catalytic transformation for some cases. So if the SDP lower bound is achievable, there is no catalytic transformation. And basically, by combining this result with the tightness for the complex conjugation, we can show that there is no catalytic transformation for the complex conjugation. Okay, so I will show you some proof techniques why you can obtain this SDP lower bound. So main idea to show this SDP is to utilize the differentiation. So suppose you have a quantum circuit implementing the function f. So basically, it is the assumption that you have this kind of sequence of unitaries v1 to vn plus 1. And this gives you the function of f. So sorry, f of u. And by defining this unitary part, blue part as du, and inserting u as e to the I epsilon h, and by differentiating epsilon, then you will obtain the below expression. So on the left-hand side, basically from the chain rule, you will obtain n terms of the that is composed of these matrices mjk, which is basically related to the unitaries v1 to vs. And from the right-hand side, you will obtain the first derivative of this function f plus some global phase, because you can have the global phase on this f of u. So there is a degree of freedom to add this kind of global phase. Okay, so you have this. Okay, from the differentiation, we obtain this expression shown in the top left. So there you have some epsilon h, and this epsilon h is related to the derivative of the function f under global phase. And this epsilon is represented by in this form, and actually this is a CP map. So we can relax condition a bit that this epsilon should satisfy this constraint, and this epsilon is CP map. And also, if we insert the identity operator on this epsilon, then you will get that the output of this epsilon map should be n times identity due to the this summation. So like the reason why n appears here is since you have n additions that comes from the chain rule. And if we write these conditions as a Choi matrix, then you will get the SDP constraint like this. So yeah, so basically in this way we can show that any protocol should satisfy this constraint. And we have some remarks. So first remark is that we only consider necessary condition, and in particular from the first so in the first step we differentiate it, and we didn't consider about the local. We just consider about the local property, but we discard the global property of the function. So it's just a necessary condition. So our argument does not imply the achievability. And the second one is that similar differentiation technique is also used in our concurrent work to show a no-go theorem for the simulation of the quantum switch, and which will be presented as a poster today. Okay, so in the remaining time, I will talk about the extensions of this work. So basically, in this work, we have considered a very specific task, which is to implement the function universally and exactly and deterministically. So we consider this very small region, and we show a no-go theorem for this region. But maybe this is overkilling for practical applications. So for instance, like usually we just need the approximate protocol, and any protocol should have some approximation error. So there's no point to exact protocol in this way. So yeah, and so to consider this kind of more practical scenarios, we have considered the relaxed setting and to show a no-go theorem for this kind of relaxed setting. So the setting of the probabilistic scenario where you can just obtain the function of f probabilistically, or the case where you have some partial information of input unitary, and this partial information is given by a subgroup of the unitary group. And we also obtain the SDP lower bound on the query complexity in this relaxed setting. And I just show you one example for probabilistic transposition case. So basically, our SDP lower bound gives a lower bound on the queries for a given success probability. So basically, in this figure, so our lower bound is represented by this this curve, black curve, and in the this x-axis is the number of queries, and the y-axis is the success probability. And basically, our no-go theorem rules out this vision, and basically any protocol should live in this part. And if we convert the point of view, basically it gives the upper bound on the success probability for a given number of queries. Okay, so I will conclude the talk. So in the first part, I show that there is a non-trivial universal transformation of unitary operations. And for this kind of task, we prove a tight, universal, and a scalable SDP lower bound for the number of queries. And the proof technique used in this work is a differentiation. And this technique can be extended to a more relaxed setting, probabilistic or partially known setting. Okay, so this is the outlook of this work. So first one is that we have derived the SDP lower bound based on the differentiation, and especially first order derivative. So it's just considered the local properties of the function f. So maybe we can obtain the tighter lower bound by considering the higher order derivatives, but are still not done. And the second one is that for the transposition, our SDP lower bound does not give you the matching lower bound. And the lower bound is linear in D, but the upper bound is D squared. So logically, there are three possibilities. One possibility is that maybe there is a unitary transposition with less queries, say linear in D. And second possibility is that maybe by improving the lower bound, we can show a tighter lower bound for unitary transposition to provide n is less larger than d square, or maybe something in between, like n to the 1.5 or something like that. Okay, thanks very much.
Thanks so much, Satoshi. That was a very nice talk. We have time for questions. There's one there.
Yeah, thank you for the talk. Can you use your technique to derive lower bounds for example, controlled unitary, from unitary to controlled unitary?
Mm-hmm. Thanks very much. So it is already known that controlled unitary is impossible. So in a sense, it's already known, and so the already known result is that lower bound is infinity in a sense. And by solving our SDP, it always gives you the finite value. So our SDP is not tight in that case.
Can you translate your probabilistic setting to approximate setting as well?
Sorry, can you say again?
Can you translate the probabilistic setting to approximate setting or back and forth?
Yes, so that is a good point. So yeah, so yes, so we also wanted to extend this result to the approximate setting, but in a proof technique, we should utilize some exact equations, and so basically we don't have a lower bound for approximate setting in this work.
Other questions? I actually have one. If you solve that SDP, what is the optimal solution? Is there any way to understand that? Because it's just a lower bound on the complexity, so it doesn't by itself doesn't give you a protocol, right?
Right. So basically, it just gives you, but it somehow like includes a partial information about the protocol. So okay, let me consider. So basically, as a result of the SDP, we obtained this operator beta, and basically this beta corresponds to this function alpha. So basically, it just gives you a partial information about what this behavior of global phase is, but other than that, it doesn't provide more information about the protocol. Yeah.
Another question here.
Yeah, thank you for the very nice talk. Have you thought about any techniques, or are there any techniques in general that show some kind of achievability results? Like, do we have a characterization of what types of transformations might actually be possible?
Mm-hmm. Yeah, thanks very much. So that is very interesting question, but unfortunately we don't have such a construction. So yeah, so only known transformation is these three transformation: inversion or transposition or complex conjugation. And basically, inversion and transposition are implemented in a very similar way, while complex conjugation is implemented in a very different way. So we don't have a very nice overview of what is a universal transformation in the sense of universal for function f. Yeah, but that is a very interesting question.
Great. Thank you very much.
Okay, then let's thank Satoshi and all the speakers of the session again. And we now continue with the poster session.